Hi everyone, this is the session 5, actually fifth session of our time series modeling and signal processing lecture series. So in here we are going to discuss the AutoArima, SARIMA and SARIMAX model and their implementation. So in last lecture we discussed ARIMA model, and previous that what is AR model, autoregressive model, and the moving average model. That integration of them called ARIMA model we discussed it. Then from here onwards we are going to discuss how do we automate them and how do we implement AutoArima and SARIMA model, as well as the implementation of SARIMA with the SARIMAX model, right? So in here what we are going to discuss is actually, so this lecture we will discuss the uh, what is the first one, AutoArima, and then SARIMA with the seasonal component, as well as implementation of the SARIMA with SARIMAX. Right? This lecture we will discuss the AutoArima, SARIMA and SARIMAX models. Right? So this is the objective of this lecture, and this is the way of we are going to discuss. Right? Then first let's see what is actually AutoArima. Right? You all know, actually you all have the idea about what is ARIMA model, right? Then in the ARIMA model we have three component basically, right? The ARIMA model we have basically three component. What are they in the ARIMA model? First part is this autoregressive part, then moving average part, then we have I, right? Then what happened in this AutoArima model, what we are going to do is actually, rather we are finding these models, there are parameters in the AR. What are the parameters we discussed in last lecture? P, right? P, then for the MA model it Q. Then in here differencing is simple T, right? Then what are the number of past data point that you are going to use in the AR model is represented by P. Then the number of previous error component that you are going to use in your MA model is represented with Q. Then the number of differencing is denoted by D, right? Then these things, actually the P, Q, we identify with the PACF and ACF graph, right? Then what happened actually in the AutoArima, we are going to automate them. Then what happened in the AutoArima, in AutoArima model, we find, right? We find the optimum parameters or values for this P, D, Q, rather going with the PACF, or ACF graph. What we did previously is we use this PACF and ACF graph to identify P and Q. Then what we did is we include this parameter value to ARIMA model. then we implement it. But in the AutoArima, what we can do is in the AutoArima finds the optimum model parameter. Actually, it could be say it can be said as a model as well as parameters, right? For P, D, and what is the other parameter is Q, right? AutoArima finds the optimum model parameters for P, D, and Q, right? Then actually we no need to use PSCF and ACF graph to identify the P and Q parameters manually. Then no need to find the P, D, and Q parameters. No need to find the values for actually values parameters manually using PSCF and ACF graphs, right? Then actually what we are going to do is using AutoArima, we are going to automate the things that basically identifying the best parameters, optimum parameter value for ARIMA model, right? Then we will discuss how do we do that, right? In order to get somewhat of understanding, what we are going to do is in ARIMA model, it's the same as the same ARIMA model. We have autoregressive part, we have moving average part, and there is an integration as well. Then the only thing that we are going to do is we automate it to identify the P, D, and Q parameter values, the optimum values for these parameters, right? Then the second thing that we are going to use is SARIMA and SARIMAX model, right? Then actually what is the SARIMA model, right? So in SARIMA model, what we are going to do is right. Let's first see what is SARIMA model. Actually, in SARIMA model, as we discussed in the ARIMA model, we are not actually focusing on seasonal component, right? We are not focusing on seasonal component. Yes, right? We are not focusing on seasonal component in the ARIMA model. But in the SARIMA model, actually, we can include this S parameter as well, the seasonal parameter to the model. Then once we add this seasonal parameter to the ARIMA model, right? To the ARIMA model, it became, to the ARIMA model, it would be the SARIMA model. Right? Then only thing that we are applying it here, the seasonal component, right? Then what was the previous parameters in this ARIMA model? We had simple P, simple D, as well as simple Q parameter. Then in here, in the SARIMA model, we have three more parameters. Actually, not three, four more parameters. Then in the SARIMA model, we can represent it as like this, right? SARIMA, it like, if I use some text, it could be like, how you can say, and P D, sorry, P D and what else, P D Q, as well as uppercase P, uppercase D, uppercase Q, and there is another parameter called M. This is how we represent SARIMA model. How do we represent a ARIMA model actually? The ARIMA model, how do we represent it? Simple P, simple D, and simple Q. The same parameters available here as well in this part, right? Then we have additional 4 parameters in here. Then let's see what are they. Actually, previously that I should say what are the things that we are going to discuss is in here. The SARIMA model, it calls actually seasonal autoregressive integrated moving average. Sorry. Stand for seasonal autoregressive integrated moving average. The seasonal component is adding, right? Actually, as I said earlier, SARIMA solves what? Actually, SARIMA is for SARIMA to solve the seasonality problem. That's what we are going with the SARIMA model in order to grab and include the seasonal component into the ARIMA model. That's what we are introducing this SARIMA model. Previously, we ignore this seasonal component. Actually, we predict it somewhat. Anyhow, let's see what happens when we add the seasonal component into this model, right? Actually, in other words, we can say that it is actually extended version of this SARIMA model, right? It's a extension, actually. It's an extension. Then we can say that actually seasonal ARIMA or SARIMA is an actually extension of what? Of ARIMA model, where what we are going to add it here is the seasonal component, where seasonal component is attached. Seasonal component is represented by capital S. What else we have discussed? Actually, let's see other parameters. Actually, I'll list them down. And what is the first one? P stand for, in here you can see the PDQ. These are available in the ARIMA model as well. Then these are non-seasonal component. Non-seasonal component. Simple P, D, and Q are non-seasonal component, whereas capital P, D, and Q and simple M are seasonal components. Actually, these capital P, D, Q are analogous to simple P, D, and Q. But I will say how it analogous. In the P, D, and Q, we consider only the data point itself. But once we consider the capital P, capital D, capital Q, it depends on this M. M is what? That's the problem, right? M is what? Let's see. First, I'll define these terms. After that, let's see what are the meaning of these parameters, right? Then as I say, P, D, and Q, these are actually non-seasonal. This is P for autoregressive part, right? Autoregressive order, AR order, simply AR order, right? Then what would be the second parameter D? It would be seasonal, non-seasonal, sorry, non-seasonal differencing, right? It's non-seasonal differencing. Then similarly, Q parameter is non-seasonal moving average oh, simply MA. Right. These are P, D, Q. These parameters you are familiar up to now. These are the things, parameters which are engaged with the non-seasonal component, non-seasonal autoregressive, non-seasonal differencing, non-seasonal moving average, right? Then the other parameters, what are they? Capital P, capital D, and capital Q. Then these are the simply that same as previous. Actually, these are seasonal AR order, right? I simply write it and repeat it here and MA order, and this is seasonal difference, right? Then the final parameter M. That's the place where we have to discuss. This is the length of repeating seasonal pattern. In other words, seasonal period. What is this? It's actually length of repeating seasonal, sorry, pattern. In other words, we can say it seasonal period, right? So I'll discuss it, right? I'll explain it. What are they, right? Let's take another. Okay. So what happen usually? Usually, suppose time series like this. I roughly draw a time series like this, right? There could be some observation. I don't even care on that. The x-axis is time parameter. Then suppose we have timestamps like this. Okay. Then suppose from here, I'll pick some places, right, in order to explain it, right? Then 1, 2, 3, 4, 1, 2, 3, 4. Sorry, it could be, it comes here, right? Then suppose it start like this. Then again the similar pattern print. Actually, sorry for the pattern, it's somewhat differ. Anyhow, I just wanted to let you know that the pattern, right? The pattern which is repeating It's similar, actually. Suppose this is a similar pattern, right? So it happened yearly. That's what actually I just want to mention. This a quarter, right? 3 quarters or 4 quarters. Then each 3 months, 4 times 3 months, it's 1 year. Then within a year, this pattern is repeating. This pattern is repeat, right? Then seasonal is, what does it mean by the seasonal component? The repetition or repeat patterns within a year, right? The less than the year, actually. That's the definition of the seasonal, right? Then it happens yearly. Then that is the meaning of this M parameter. The length of repeating seasonal pattern. In here, then M would be, with our example for the, according to this, it would be 12, right? It would be 12. As example, if we take like this, as example, uh, suppose if the period of time series, sorry, of time series equals to 12, actually it can be represented or rewrite like this manner, right? It can be denoted as like this. How do we say it? I'll copy this. It's easy for me. Then we know that if the time period of the time series is equal to 2, which means that repetition happen within year. Suppose it's a monthly data, then 12 in the sense 12 months, then M would be what? M would be 12, right? Actually, I have to add ER here, otherwise it's in the same line. It's quite low. Then in the SARIMA, what we discuss is SARIMA, we implement this or we introduce the SARIMA model in order to address the seasonal component of our time series. Basically, previously, without having the seasonal component, we model the time series using ARIMA model. Then the SARIMA model we introduced to engage the seasonal component as well. Then it became that existing ARIMA model become SARIMA model with the S component, with the seasonal component. Then the existing three parameters of the SARIMA model is already there. That is lowercase p, d, and q. These parameters are non-seasonal component, right? Non-seasonal parameters which are engaged with respectively autoregressive order, differencing, as well as moving average. We already discussed it, right? Then the problem is these remaining three parameters: uppercase P, D, Q, and lowercase m. I said the P, D, Q analogous to the simple PDQ similar way, but there is another component is called simple m or lowercase m. The lowercase m is the place where we are saying this, the length of this seasonal component is available. The period, time period, seasonal period, right? Then with this example, the same similar seasonality is repeating in each year, which means each 12 months. That's what I say. If the period of the time series equal to 12, which means 12 months, we can say that M is 12, right? That's clear, right? Then what would be this P, D, and Q? There is also a problem. I'll explain it as well. Suppose like this, right? We have a line, right? T equal 1, right? t equal 1 to suppose t equal say 24, t equal 24, right? In between we have multiple timestamps. Then we have altogether 7 parameters in our SARIMAX model, right? In the SARIMA model, what are they? Simple PDQ3, capital PDQ3, and simple M. Altogether 7 parameters. We already know what is this P, D, and Q, lowercase p, d, q, which means the P stand for previous data points which are for autoregressive part, which are for AR. Previous data point, in that case, this, like that. Same as the simple Q, previous error component for what? Moving average mode. Okay. Then it's also similarly previous, blah, blah. Okay. Right. Then what happened in I in the sense in here D, right? Simple D, the differencing, what happened? Differencing by what? Like this, right? In the differencing with the previous time, is shifting with the previous. We implemented them, right? Then with the previous timestamp. Then once it comes to SARIMA capital P or uppercase P, uppercase D, and uppercase Q. What happened? That's the problem. There, what happened? Right. Okay, then let's discuss this with initiating with the seasonal difference, right? That is, this lowercase d is just differencing, right? Just differencing. But in here, it's seasonal difference. It is seasonal difference. I'll explain it. Then let's take another small title for that. Seasonal. Right. So what is the seasonal differencing? How do we represent it? Right. We can actually represent it previously. How do we do it? Actually, what we did is previously yt equal, sorry, t minus 1. Likewise, in here, what we can do is once it comes with the seasonal component, the equation would be like this, right? How it would be? The equation would be like this. Delta M with the seasonal component, right? Then y sub t equal sub t minus y sub t minus a. It would be t minus m, which means rather considering as previously that just previous timestamp or data point, what we are doing is we are considering the with the time period, seasonal time period. For example, if the seasonal time period, suppose m equal to 12, right? if we are in here, in this place, it differencing with the seasonal period, which means it goes not to the previous one. It not goes to here, but it goes to the way around here. The length should be 12. Length should be 12. That's the seasonal difference. How do we say it? For example, if I write it in the letter or word, suppose D equal 1, right? Then what happened? Then what we can do is we can difference y sub t once, we can difference y sub t using the seasonal period. Using the seasonal period, how do we write it? We can actually difference y sub t. We can difference y sub t only once, right? Once, because d is 1. D is 1, then once, right? Once using the seasonal period. Using seasonal period. But what happened in that normal difference? What happened in the regular differencing? In the regular differencing, right? In the regular differencing, as we discussed in here, right? In the regular differencing, we just subtract with the previous sign stamp, only one. But in here, it jumps with the length of the seasonal period. Length of seasonal period. Then in the regular, right? Regular differencing, we usually do is we usually subtract, right? Subtract one time step, right? Only one time step, instead seasonal period. That's the difference. Right? That's the difference. Right. What happened once the capital D equal to 1, in the sense we are differencing only once with the seasonal period. If the seasonal period is 12, we differencing with the previous length of 12 period, right? One, but in the regular differencing, we are once d equal 1. If that simple d equal 1, in here actually the regular differencing, suppose d equal 1, capital, sorry, simple d equal 1, then we subtract only one time step. Then actually, for example, we can say that suppose for this example, if the d if the d equal 1, and suppose we have monthly data, and t equal suppose month of April, right? Then once the d equal 1, the t equal April, then differencing by 1, seasonal differencing by 1, in the sense we are subtracting, we subtract from the previous April value, right? That's what happened actually. Suppose in here, this is month April, then it differencing once d equal 1 in the sense you have to jump the previous year April, not the previous time step itself. You have to jump into the previous year April value, then you have to subtract, right? I think it's clear enough to understand what is the difference between normal regular uh, differencing as well as seasonal differencing. In the seasonal differencing, what we are doing is we are subtracting the value by identifying with the seasonal component. If the seasonal component is 5, you have to subtract with the, you have to skip the 5 data point previously, then you have to subtract, right? Likewise. Then this is seasonal differencing. Then there are two more components, right? Seasonal AR model and seasonal MA model. We discuss D, seasonal differencing, and we discuss what is a M, right? Simple M. So what happened with the seasonal AR and seasonal MA model? Actually, in first one is AR model, right? The AR part, so I think you can remember the normal autoregressive one, right? Just forget about the seasonal or whatever the things. Then what was the equation for this normal autoregressive part? What was the equation? What was the equation? It was like this, right? So yt equal bias term, then noise term, epsilon t, then what was there previously? Then alpha 1, what else? Y t minus 1 plus alpha 2 y t minus 2 plus blah 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 blah, then plus, sorry, alpha p y t minus p. Right, then just think based on the seasonal component, a seasonal period value, how do we restructure this formula, this AR1? How can we restructure this formula with this M component? Then because we discussed this, so we discussed this seasonal differencing. Then normal differencing, what we did, if the simple d equal to 1, we subtract the previous value, only just one previous value. Then one is to come to that capital D equal to 1. Then we consider the seasonal period. We identify what is the period where this seasonal component is iterating. Then in our example, we said that it is 12 months. Then seasonal differencing with d equal 1 in the sense you have to difference the time point where you are right now at with the previous value, which is length of 12 months. Then suppose this month is December, then you have to subtract the previous year December value instead of the November value. That's the simple one. Then how do we can rewrite this similar equation this for that seasonal one. How do we can rewrite? It can be write like this, right? We have our yt, right? Y sub t. Then we have normal bias term. Then epsilon term, right? Normal epsilon term, right? Then epsilon t plus what else? We have alpha 1, and that's the problem where we have to incorporate the seasonal compound. We can write y sub t minus m. Like this. Instead of this t minus 1, t minus 2, t minus 3, t minus 4, blah, 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 we have to replace this part with the seasonal time period with m. That's the only difference. Then if we write it further, it would be like this. Then it should be 2 times m. Then what would be the final component? Alpha, this would be alpha 2, alpha p, p times m. I think you get the point. We can simply say it like this. Actually, what happened to y sub t is actually depend or it regress on usually past data point, right? Past data point, but in the time series at multiples in away actually depend with the past data point. In the autoregressive part, you know that it depend with the past data point, right? But the way of identifying past data point is differ based on normal ARIMA and this SARIMA model. In the normal ARIMA model, how do we identify the previous timestamp or time point? Just this previous data point, just previous data point, right? But now we have to jump with the previous data points with what? With the m parameter, with the m or seasonal period instead of by 1, right? That's what I mentioned in here. YT regress on past data points in the time series at multiples m away from t, right? Okay, that's the AR part. Then how do we write this MA part? How do we write this MA part then? What is the MA or moving average? What is the moving average? It depends what? Previous error in the time series. Then I just copy this one. Then I'll change it like this way. That bias component like C epsilon, instead of epsilon, what we use is theta, right? Should be Q. Because in the moving average part, we consider in the previous error component, right? Then the similar way as previous, we have to consider the time differencing based on the seasonal period, not just the previous timestamp. That's the only thing you have to keep in your mind. Then actually we can rewrite the same thing in here as well, right? Same thing. YT regress or depend on past, not data points, past errors. Errors in the time series at multiple anywhere from the target. The only thing you have to keep in your mind in this SARIMA model, when compared with the ARIMA model, in the differencing, which means capital D and order of seasonal autoregressive, capital P, and the order of moving average of seasonal moving average, capital Q, you have to consider the M, the value of M, which means seasonal period, the duration where the seasonal component happening. Then you have to identify that, right? You have to identify that. Then you have to substitute this value to M. Then once you consider the order, which means POD values or POQ value, capital POQ value or capital D value for the differencing, you have to jump based on this M value instead of just one. That's the only thing you have to keep in your mind. Right? Then, as a summary, what we can write the SARIMA model. Actually, SARIMA model is the SARIMA model is the composition of AR component as well as MA component, but in two different ways. What is these two different? One is seasonal, other one is non-seasonal. Then if we write it this manner, SARIMA is the two component, right? Seasonal AR component which multiplied by the non-seasonal AR component added to the seasonal, so MA component multiplied by the what? Non-seasonal MA component. Then it simply, we can write it like this. The SARIMA is the seasonal AR component. seasonal AR component multiplied with the non-seasonal AR component, then added to the seasonal MA component and non-seasonal MA component. Actually, that's this equation, or actually this model, right? It's actually extension of this ARIMA model by adding the seasonal component to simulate or to identify the seasonal behavioral patterns of our time series data. Then we are adding these 4 more parameters to the model in order to build the SARIMA model. What are these parameters? Uppercase P, D, Q, and lowercase m. Then M stand for that seasonal period, which means the time duration where the seasonal component repeating. Then P stand for the seasonal autoregressive order. Q stand for seasonal moving average order. D stand for seasonal differencing. Right? Okay, clear. Then let's see how do we implement this with the model implementation, right? The model implementation is called SARIMAX. There is an additional letter, this X. There is an additional letter, this X. Actually, we can pronounce it like this. It's actually as previous, seasonal auto regressive integrated moving average with what? With exogenous factor. It write like this. Spellings is correct. Yeah. The X stand for this. Then what is this X? The name is exogenous factor. That's right. Then what does it mean? Actually, it means, suppose like this. If you want to add some additional value or parameter or any other variables which is parallel time series, it could be parallel time series, then you can use this X component to add this. Actually, it is not in this scope, because in this scope we are discussing about univariate time series. Then I am not discussing further of this exogenous factor, right? But I just mentioned it here. What is this exogenous factor to get somewhat of understanding, right? Actually, if I write it, it's like this in this time series. We can say the X factor or exogenous factor is, or could be a actually a parallel time series, right? Time series where it directly not modeled with this our time series, right? But we can include this value into this time series as an additional factor. For example, suppose stock price. Stock price, if we consider stock price as a time series, right? What happen usually? then it's highly fluctuation, right? Sorry for this, right? Like this, it's fluctuating. Then once we modeling this with the time series data, what we are doing is we are considering this previous time points, previous error component, and the seasonal patterns and things only with the univariate, which means depending on the same data set or same time series. But suppose actually there are minimum factors, right? Like if the macroeconomics variables, fiscal policy, and things like that in the government, if there is any some uh, issues arise in the political factors, there are so many qualitative and quantitative factors are affecting to this. But these things we are unable to include in the ARIMA model. But in the SARIMAX model, that X is representing these kind of stuff, actually, which are not directly involving in this our model, but we can feed this data into this model using this X parameter. Then how do we write this? In this time series, the exogenous factor could be a parallel time series. Actually, it is not modeled directly, but we can use as a weighted input or input to our model using this X, right? Then how do we write this? In this time series, the external factor could be a parallel time series. Parallel time series. Then that are not actually not directly not modeled. Directly with our time series, but we can incorporate it, but is used as a weighted input to the model, right? Then what we can do is using this exogenous factor or X, we can input some additional parameters or some additional data or some additional time series into this model as a weighted input. That's what we use this X component, right? Okay. Then we discussed that SARIMAX is the way of implementing that SARIMA model in the Python code or whatever the code. Then S stand for seasonal component, ARIMA is stand for ARIMA, we discuss it. Then X stand for exogenous factor, we discuss it as well. Then this is the model. Then this is a machine learning model, right? This is a machine learning model. Then once you know that as a data science student, in a machine learning model, there is a process called model selection, right? The optimum model we have to choose, right? Once we implement in this, we have to choose the optimum model, right? Then in this circumstance or in this aspect, how do we identify it? How do we identify the best fit model? Right? That's called actually the model selection. Let's discuss how do we select it, right? Right. Then what we did previously in order to identify these best fit parameters, how did we perform it? We implement ACF and PACF graph so that we will be able to identify the autoregressive order as well as moving average order based on this two graph, ACF and PACF graph. But I said earlier, when we start the session, the AutoArima is going to identify these parameters automatically rather worrying about this manual process, right? Then what we are going to do is actually previously what we have done. Previously, what we perform previously, actually we perform ACF and what is other PACF to identify the parameter values, right? Parameter values of the what? Of the ARIMA model, right? Of the ARIMA model. But now what we are going to do is, but in auto ARIMA, what we are going to do is the best fit model will be selected or choose automatically. Right. In order to do this, there should be some criteria, right? There should be some way. Then once we selecting a model, what kind of a things that we want to consider as a machine learning aspect? What kind of a stuff? Actually, once we selecting the optimum model, there is a trade-off. There is a trade-off between what? Between the model complexity and the model accuracy. There is a once we model selection process, definitely, right? There is a trade-off, right? There is a trade-off between what? Between model complexity and the accuracy. Accuracy. When building the machine learning models. That obvious, right? Then what does it mean, model complexity and accuracy? You simply know that. What is the model complexity? The parameters, right? For this circumstance, in our case, for ARIMA model, sorry, for ARIMA model, the complexity would be what? Increase the P and so P and Q, right? P and Q, which mean large past data points and their components. If we draw it like this, there is a time series, right? Then if suppose there are multiple time points, timestamps, right? Then if P getting larger, P increase, P and Q increase, getting increase, which means suppose we are right now at this place, then suppose P equal 5 in the sense we considering up to this. 1, 2, 3, 4, sorry, up to this. Then suppose P set to 10, which means it goes further in this way, which means the data set is higher, which means the large past data points. Then Q is also go similarly. Then the complexity is getting higher, right? But actually, usually we know that when data increased, the model accuracy will also be enhanced or increased. Usually it happen, right? But in the complexity perspective, it is better to identify that over what is called a optimum point where this trade-off can be equilibriums. For example, I think you may familiar with overfitting, the term overfitting, right? For example, suppose it's graphically, we can represent it like this, right? Suppose this is the model complexity. Model complexity. Complexity. And this is the error. This is normal, usual machine learning stuff, right? In the model selection process. So what is overfitting? Actually, for example, suppose usually suppose this is a training error. I just use TE, right? Training error. Getting lower, getting decreased. Then suppose testing error like this. Then it getting increased. This is testing error, test error, right? Test error. Right. This is the test error. Then if we divide this from here, you can see in here it's getting increased the test error, right? But training error it's getting decreased because model complexity is too high, which means we are increasing the past data points and past data component. Then it's well trained, well trained. But the testing error or test error getting increased again, it's getting lower, then increase. Then can you imagine these two sides? This side is overfitting or this side is overfitting? Yes, this side is overfitting. This is overfitting area because it trained with the training data properly, but not perform with the testing data. Actually, the model is not good. Then this is called actually underfitting area. Then actually in here, it's somewhat actually it could come here, right? Sorry for that. We can get it here. That's fine actually, like here. Then it would be actually best fit or optimal. Best fit or optimal. Right. Then here, that's what I say. There is a trade-off with the accuracy as well as model complexity. The past data pointers, number of parameters that we are using. Right. Then we want to identify that optimum place. Right. We want to identify this optimum place. Right. That's what we are going to discuss in here. Right. Then what we have written here for ARIMA model, complexity increase the P and Q, right? Once we are considering this ARIMA model, we have P and Q, that large past data point, right? Then, in order to identify that optimum model, what we have to do is actually usually what happens? Usually, when data is increased, right? The model accuracy will also be enhanced, right? Will also be enhanced, but it is better to identify the optimum as I shown in here. This is the optimum place, optimum parameter or model complexity in order to address the trade-off. Right. The way of doing this in the context of this ARIMA or SARIMA model, we use AIC. We use AIC, right? That is the default model selection, the way of selecting the model, right? That's called AIK information criteria, AIC, right? Actually, this is the default one in the ARIMA, in the auto ARIMA. In the auto ARIMA, right, uses this AIZ by default to select the best fit model. Best fit model, right? This AIC is a score, right? It's implemented, actually it has been implemented in the mathematical model to evaluate the model and identify what is the best fit model out of several models, right? In the auto ARIMA, defaultly, that usual way, it use this AIC to determine the best fit model, right? Then actually the AIC is a mathematical model, right? Mathematical actually method which what does it do? Which uses to compare different models, right? Different models and determine which is the best fit model. The available data. Right. Okay. So up to now, what we have discussed, the objective of this lecture is to implement and get understanding on auto ARIMA, SARIMA and SARIMAX models, right? Then we already know what is the ARIMA model. Then in the auto ARIMA, what we are going to do is we are going to automatically identify the parameters instead the manual process of PACF and ACF graphs. Then we discuss the SARIMA model and its parameters and what is the purpose and how do we define them, how do we interpret them, how do we incorporate them with the model and things like that, right? Then we discuss how do we select the model in the context of auto ARIMA and what is the criteria that we are using to identify the best fit model. That is called AIC, right? Based on that, we can identify what is the best fit model with the multiple parameter lists, right? Then we discuss what is our best fit model and what is the overfitting and what is the underfitting and things like that, right? Then this is the time to implement this model, right? Then let's see what is the way of implementing this. I'll write this model implementation. Okay, right. Then I'll copy some thing from previous code. Otherwise, it time consuming that important import statements like this. What we want to get some cells. Otherwise, it's difficult, right? Then pandas we want numpy and things. Then this is the special case that I am importing in here. That is called PDM ARIMA. This model, this library is the one you have to use to model this auto ARIMA, right? You can add it using pip install, right? This PDM ARIMA, and I import it as a PM, right? All others are we have discussed previously as well. Then the usual way I import my previous the same data set, right? Same data set I'm importing. Okay. Then I just go a little bit faster, right? Then I'm defining another column in here. Before that, let's say whether it's import properly. Right, okay, cool. Then I'm preparing another column, log OBS, log observations. Then how do we do that? Sorry, log tf dot observation, right? Observation. Let's see again what happened with the head. Okay, actually I get this. I just want to compare this log observation and normal observation value without logging the performance of the model, right? Because previously also we did the same thing with the log observations and the normal observation, and most probably that log observation could get the better predictive accuracies, right? Prediction accuracy in the previous cases with the ARIMA model. Then let's check whether that same thing happened in here as well, right? Because right now we are adding the seasonal component as well, so that we will check whether there is some improvement or there is some issue or what could happen, right? That's what I initially create these two columns. Actually, not two columns. Existing column is observation. Then based on that, I get the log observation as well. Right. Good. Then, as usual, I split this data set into two, and I'm going to predict next 12 months. Then the number of prediction would be 12, right? Then the train size would be df dot ilog. Then I go into the all data points from here to minus n tests. N minus n, right? Then test, I'm going to I copy the same code here, right? Instead of it here, I put in this side from here to the rest of, then it actually 12. Okay, right. Then I'm going to implement the model, right? Then I get this variable model, then I'm importing with this PM reference. It called auto ARIMA. You can suggest it. Then I'm going to include some parameters here. What are these? First, the data that we are going to include there. I'm going to include that train observation, that raw data points, right? Then there are several other parameters as well. The trace true in order to trace the logs and things, right? Trace, I set it to true. Then suppress warning, actually these are suppress warning. I set it to true. If there is any warning, I can see them. Then another key component, seasonal. I set it to true because that's what we are going to do in this model. Then we have to mention the M parameters, the seasonal period. I set it to 12 because in the previous, what is called uh, data exploration, we have, because we have used this data set for these 3 to 4 lectures, then we had some understanding on this data. Then I set this M in the sense length of the seasonal component, which means that the seasonal period into 12. Then seasonal I set to true, right? This is how I am implementing this auto ARIMA model. Then I am training the model with train observation, this raw data, right? Okay. Then I'll run the model. See, you can see this AIC is displaying here. That's what I mentioned. This AIC is the criteria to identify the best fit model in the auto ARIMA. And you can see in the ARIMA, there are these parameters, right? P, D, Q. All are these non-seasonal parameters. Simple P, simple D, simple Q. And these are the seasonal parameters, that capital P or uppercase P, uppercase D, uppercase Q, right? This is the seasonal period 12 that we mentioned, right? Seasonal period. Then you can see this AIC score, and right, they say that best model ARIMA 312111212. So the total fit time, don't worry on this, we don't need that actually. ARIMA 312 312 it's here. 312 312 112. There are multiple, right? Here, here, and there. Then what we can do is I'll print the model summary so that I can clearly identify what is that best fit model. Right, then let's see. The model is SARIMA 312 times 112, the time period is 12. Then the difference in that order of capital Q is 2. That seasonal differencing is 1. Seasonal autoregressive part is 1. Then the normal autoregressive part is 3. Normal difference in regular differencing is 1, as well as normal moving average part is 2, which means that there is three previous time step engaged with the ARP model, then one differencing, and 2 previous error component are considering with the non-seasonal ARIMA model. Then in the seasonal component, we have one previous autoregressive part, order 1, which means the previous year 1, differencing by 1 and differencing by 1, as well as auto moving average is also 2, which means that order 2. Then you can see that AIC is, this best model AIC is 417, 708, 417, 708. Then let's see. 407. Right. This is the best fit model. This is the best fit model. The minimum score of this 470. Check whether there is any lesser AIC value. No, this is the lowest value, right? Then we have the model. Actually, that's what actually previously what we do is we run ACF graph, we run PACF graph, then we identify uh, P value, Q value, then we substitute into the model and so on and so forth. But in here, the best model with the parameters, they are returning like this. Then we have this model. Then what we have to do is we have to make the prediction, right? We have to make the prediction. Then let's see what happened. Then I'm going to get a test spread and this as a confident interval so that I can draw the graph with the shaded areas as well with the confident interval, right? Confident interval I'll take and model dot predict. Then there are several parameters and periods. Actually, it's the number of our test data. It's equal to 12, which means n. Then we want to collect the confident interval, then return confident interval true. I set it to true. Then I can collect it to here. Okay, right. Right. Then I'm going to draw this into a graph, right? I get a figure, then axis, then PLT plot, and I can get a subplot with figure size. Fig size actually, not suggesting, I don't know why. I set it to 16 column and 8 rows. Then what else I want? Then I am going to set that AX axis with the plots. Then this I'll set to the, because with the test data, then test indexes, I set is the X. Then test observation, we are going with the test observations, right? Raw data. Then I set this label as axis label as not axis axis, this line, right? This line, actually, this is the actual value. Actual value with the test data. Then I copy the same thing because I want to go with the predicted values as well. Test index, it's right. Observation, not the observation, test predicts. Right, it should be test predict. This is forecast. Let's do forecast. Right. Then I'm going to include this confident interval as a shaded areas so that you can get a clear picture. Then I use this fill between. It is not suggesting. I don't know why. Fill between, where I'm going to fill this test index. Then I have confident interval from all rows from 0 column and confident interval with all rows of, sorry, there should be a comma. Okay. Right, I set the color of this shade color. Do I set it to red? Then I set alpha to make some transparent to 0.3. You can change them, right? Then I set legends. Right. Uh, let's run and check whether there is issue. Fit adds upload. Adds upload. Adds up. I see. It should be subplots. Okay. Right. This is the shaded area with the confident interval. Then what is called this blue color one is actual, and the orange color one is forecasted value. Right. Actually, in here it's trained well, but in the latter part there is some issue, right? But this is the real observation, right? With the real observation for the test data, right? Only for the test data. Then let's see what happened to that training data. Then I get it says a train prediction, right? Then model, I'm going to predict for, sorry, I don't want this because it's already there. Then predict in sample, I can call this function simply. Then I copy the previous one again, this one. I'm going to put it here. Then figure size no need to change. In order to test, it should be a train. Then actually I'm going to plot all the data in conjunction in here, right? Then DF observation label is actual, that's fine. That then train data, because we already have test data, then I have to incorporate train data, train indexes, then train predictions. Then this is train, right? This is train, and test indexes I'm going to concatenate. Then test prediction label is fine, blah 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 blah. Okay, let's see. Right, actually there are some differences. Anyhow, it's not bad model. You can see it's identify the pattern clearly. The seasonal component is also clearly. You can see that initially there is some lag, right? This part actually it happened. What's the reason to this? Actually, it's going with the seasonal component, 12-month seasonal period. Then initial there is no previous 12 months from here to previous, then it's that's what it happened here. But anyhow, it says some quite reasonable, right? Yes. Okay, then let's see what happened with the logs observation. Let's see what happened with the log observation. I just copy this previous code self, otherwise, yes. Right. Now what I'm going to do, then instead of a row observation, what I'm going to do is a log observation, then trace to blah blah, it's fine, it's okay. Then I'm going to run the model. Then on that I just copy this part. It's easy for me, right? And yeah, let's see, it's running. Then there are some parameters like sequence type and right. In that case, the best model ARIMA 011102. Previously it was, what is the best fit? 312 112. Right, there are some differences. Let's see what happened actually. Then there is no autoregressive part. One differencing order one of moving average in the non-seasonal components. In the seasonal component, 1, 0, 1, or 2, something like this. Right. Then let's do the same thing again for to collect this test prediction. I'll go with a test spread with log and log right. Okay, then we will draw it and let's see what happens. Let's upload test index should be log observation test predict log confident color that's fine then. Not much better. Right. Okay, then let's see the training data then as previously. Training data predictions. Training data prediction with log. Then I run it. Then I copy this code block again. Then logs observation. Train pred log test trade log confident interval log alpha 3 forecast 5. Once we run this, actually in here it's, let's compare with the previous. It's a little bit difficult to get a clear understanding of seeing this image itself. Then I'm going to use some matrices, error matrices, matrices to evaluate the model, right? Then therefore we will go with the root mean squared errors. Root mean squared errors, then I pass the t and y. Then I return what? NP. I have to get the square root. It is not suggesting square root, right? Then what I have to do is I have to get the mean of what? Mean of t minus y for the 2. Right. Then I'm going to print, then I'm going to print non-log root mean squared error. RMSC I pass test observations and test prediction, right? Test prediction, this is for non-log. Then go with the log ones. Log observation, test spread. Sorry, we have to actually use the exponential, right? Because it's a log value, then we have to use this NLP. We see. Yeah, that's what happened. What happened actually in the log observation, log value, we have higher root mean squared error. With the non-log data perform well in this circumstance. But previously for last lectures, actually we get much more high accuracy with log data. But in this case, it failed. Why is that? In this case, actually, most probably the suspicious place could be that once we are adding the seasonal component and other parameters, the best fit one is go with this non-log data, with the real observation, rather going with the log observation. That could happen actually. That's what to say. We have to measure it, we have to tune it, we have to identify the a proper data set as well as that scaling method and everything, right? So this is how we perform this. Then actually I just wanted to let you know that how do we implement these kind of a stuff, right? The easiest way. Then throughout this lecture, what we have discussed is we have discussed auto ARIMA. Then how do we implement it? Then what is the SARIMA and how do we implement it with the SARIMAX model? Then what is the seasonal component and how do we interpret it? What are the parameters, additional parameters of this SARIMA model? And in addition to the ARIMA model, this uppercase P, D, Q and lowercase m, we interpret them, we discuss them, and what is the seasonal differencing and seasonal AR and MA model, how do we interpret them, and how do we select the model with AIC, and how do we skip ACF and PCF graph in order to identify that P and Q parameters in non-seasonal ARIMA model, and the way of implementing this auto ARIMA, and two different approach with the real observation and log observation. How do we interpret these AIC values and how do we identify that best fit parameters and things, right? Then how do we plot them, and based on that, how do we identify that best fit model and things like that. So that's all for this lecture with the auto ARIMA model, right? So thank you very much, you all, and let's meet in the next lecture.